Epitaxy, high temperature epitaxy and low temperature epitaxy. Do I qualify? Well, after 60 years of epitaxy, I attended 45 years actively. At the moment I'm retired, I'm still doing a little bit of consulting. I used to be employed the first half of my career at ASMI it is now, but those days it was only ASM, where I worked in CVD and where I fathered the epsilon reactor, of which we have two in the clean room in a moment. And the second half of my career was at a Philips research lab, where I introduced silicon germane in the epsilon reactor. And yeah, it's up to you whether or not that makes me qualified. Conventional epitaxy to start with. Why and how? I have to tell you a little bit about CVD in order to understand what's going on. And a couple of issues we used to have and still have in the epitaxy process: pre-epi treatments, auto-doping, and wafer slip. What is epitaxy? Well, you know that, I believe. It's growth of a single crystal layer upon the surface of a single crystal. And you do it in such a way that a lattice is continued. So if you do it correctly, you cannot determine any difference between the original substrate and the layer that you put on top. That is not a common situation. Usually you add dope, or you change the doping level, and that tells you where the interface was. We have silicon on silicon, whole epitaxy, layer and substrate are of the same material. There's also heteroepitaxy, in our case silicon germane on silicon, and the layer and the substrate are chemically different. Why do we use silicon epitaxy? Well, it solved the problem with bipolar transistors. Remember, in the old days, I'm talking about the early 60s now, there was only bipolar processing. And bipolar processing suffers from contradictory requirements. On one hand, it requires a high breakdown voltage, and on the other hand, it requires a low collector resistance. How do we solve that? By means of an epitaxial layer. Here's a substrate, arsenic buried layers that are diffused in the substrate, and now we put a lightly doped epilayer on top. Then the transistor is made in the epilayer. The high resistivity of the epilayer provides the high breakdown, and there is a low current path through the buried layer that allows you to draw a lot of current through the transistor without a voltage drop, without too much of a voltage drop. There is a third advantage, which is not very important for bipolar processing. The epilayer is a lot cleaner than the susceptor usually is. It does not contain oxygen, it does not contain carbon, and it is, in that respect, it is a better quality layer. Much later, MOS technology came along. I'm talking about the 80s now, early 80s of the last century. The MOS processes always could do without epi until the circuits got more and more complicated, and then suddenly it was decided that even the MOS devices would benefit from an epi layer. What benefits do we have? That's subsuppression. What is that sub? In a MOS structure you have PN-PN structures. Due to a voltage spike, they can get into conduction, and the only way to get them out of conduction is to remove the supply current. If you introduce an epi layer, if you use an epi layer in the MOS circuit, so P on P plus, that is not a problem anymore. Soft error reduction. What is soft error? Memory bits can turn states from 1 into 0, or from 0 into a 1 due to high energy radiation like cosmic particles, but more common are alpha particles from the encapsulation material. That is reduced, in fact, with the ratio of the thickness of the p-type layer to the thickness of the substrate. in that ratio by an epi layer. And the same advantage we already had is the bipolar processing, oxygen and carbon free layer. But that is a lot more important in MOS processing, because MOS, one of the issues in MOS, at least during those days, was the gate oxide quality. And in order to have a good quality gate oxide, you need a very clean layer, and that is exactly what an epi layer is. How do we do it? In CVD reactor. CVD stands for chemical vapor deposition. In principle, a quartz process tube, rectangular, and here, and in the tube is a slab of carbon. And if you want to work clean, the carbon slab is coated with, for instance, silicon carbide. On top of the slab of carbon are the silicon wafers, and they are heated by, for instance, an RF coil around the tube, by radiation lamps around the tube, or even by a resistive heating, and resistive heater inside the slab of carbon. This kind of reactor in the early days was used for any CVD process: oxide, nitride, polysilicon, and epitaxy. And those processes deviated a lot in temperature, so which of course for epitaxy we needed very high temperatures, and that was usually done by either an RF coil heating or by lamps. Operated at atmospheric pressure, characterized by a rather high growth rate. Cold wall process means you get deposition preferably only on the susceptor and your wafers, and not on the tube. Because if you use a lamp radiation, the lamps have to be able to radiate through the quartz, and if you coat the quartz, that doesn't run anymore. So a cooled process tube, low wafer capacity, because you cannot extend the size of the tube enormously. Deposition uniformity, pretty terrible, but in those days sufficient. And a very high gas consumption, because you're working with a very high hydrogen gas flow, and in the gas flow you introduce the silicon precursor. Used for some 20 years, this kind of reactor. Then its role was taken over, it's totally obsolete now. Then its role was taken over by the workhorse of the industry, the barrel reactor. You immediately recognize the old horizontal, only 90 degrees turned. It is a bell jar, upside down. Inside the bell jar is a pyramid, and on the sides of the pyramid you have wafers. But the gas flow is still parallel to the wafer surface. So it is in fact the old horizontal reactor, but a little bit smarter put together. This one is running at atmospheric pressure, also reduced pressure is possible due to the shape of the bell jar, and heating by either infrared tungsten halogen lamps or by an RF coil around the bell jar. We used this one for some 15 years intensively, say from 74, 75 to 1990 about. Not practical for large wafer diameters, because when the wafer diameter expands you get less and less faces on your pyramid and your capacity shrinks. Layer uniformity was better than in the old horizontal, because the pyramid was rotating, but still not great. And for 150 millimeters wafer and up, inferior to the single wafer reactor, even in terms of cost per wafer. So this one you will still be able to find it if you look around in production here and there, but it's becoming extinct, maybe it's already extinct. And then the last one, quite a deviation from what we had before. You still recognize the horizontal reactor. This is the reactor part. I did not draw, it's heated by infrared tungsten lamps that are not on the drawing. Single wafer, quite a deviation from what we had, because till that time we had batch reactors. Rotating susceptor, a single wafer, so extremely good uniformity. And another important deviation from the former reactors, the reactor is separated from the outside world by two stages. There is a load lock and there is a transfer chamber, and I will point out later that that is a rather important deviation, a rather important feature. And it's automated. There is a wafer pickup here, and it automatically loads and unloads the wafer, whereas the old reactors still had to be manually loaded and unloaded. Growth characteristic. Conventional EPI is characterized by an extremely high temperature, wrote down 1000 to 1200 degrees. It was closer to 1200 than 2000, and in any case over 1100. Very thick layers, 100 micron for power devices, but even the standard bipolar circuit in the early days was 20 to 30 microns thick. Now we are moving to smaller dimensions and to high frequencies, and the layer that once was 20 to 30 micron shrunk for the most advanced devices, shrunk already to 1 micron or even below. Using a high hydrogen carrier gas flow, I mentioned that already. You need a reducing environment. If you use as a precursor silicon tetrachloride, it needs to be reduced to release the silicon ore as a HCl3. And the high flow rate, you need a high flow rate to counteract gas depletion. The gas is reacting, you're losing, the concentration of your reactant is going down. You have to make up for that. We are moving to lower temperatures, and at lower temperatures other carrier gases than hydrogen may be possible. But remember, temperatures over 900 you cannot use nitrogen because you will grow nitride on the wafer, even a thin layer. And helium and argon are a little bit expensive to use, so hydrogen is still a good choice, and it's possible to obtain it and the quality you need. P-type EPI is obtained by adding the appropriate amount of diborane. N-type EPI you get by adding either phosphine or arsine. Arsine has the preference, it diffuses slower and has a higher solubility. And, I come to that later, is by far the worst in terms of water doping. The growth rate in general is determined by the silicon to hydrogen ratio, simply by the concentration of the silicon precursor in the gas. And the dopant concentration is determined by the dopant to silicon gas ratio. Simple, straightforward. And I sidestep a few slides to chemical vapor deposition in general. I want to explain a few things that makes what follows a little bit better to understand. What is chemical vapor deposition? Vapor phase chemicals containing the required constituents decompose and react at a heated surface to form a solid film. Variables, temperature, pressure, gas flow, concentration, and probably a few more. Advantages over other techniques: high purity, because you're working from gases. Good film stoichiometry. It's flexible and it has good economy compared to other techniques. Now, the surface reactions, characterized by adsorption. The adsorbed species move across the surface diffusion. They form nuclei, stable nucleus growth, and finally there is coalescence, and then you end up with a continuous film. The nuclei, by the way, have to reach a certain critical radius before they are stable. So you form nuclei, but most of them disappear. Only a few of them manage to reach the critical size, and they expand and grow on. Adsorption. Vis-adsorption by van der Waals forces, the species are still moving around the surface. Chemosorption is a really strong bond because there has been electron transfer. And a CVD grown film can be amorphous, like for instance silicon oxide, silicon nitride, polycrystalline, polysilicon, or epitaxy. What are the rate determining steps in chemical vapor deposition, CVD? Well, here are the steps I just described. What you have to bear in mind is that the gas flows through the reactor is laminar, flows in layers. And in a laminar flow there is very little transport in the vertical direction. The transport is from diffusion and a little bit convection. So your active species have to diffuse to the surface. They are adsorbed, surface diffusion, desorption, the reactor reaction byproducts have to desorb from the surface and have to be carried away in the process gas flow. The surface adsorption is followed by specific reactions, and the gas, well, in an ideal case, of course, we only have reaction at the surface of the wafer, the surface of the receptor, at a heated surface. Why don't we suffer from gas phase reactions? Because we use a lot of dilution. There's always a very high hydrogen flow compared to the silicon precursor. And doing it that way, you can exclude gas phase reactions which would cause defects, silicon particles raining on the surface. And you can choose the conditions in such a way that there's only reaction going on at the surface. What you have to realize that each one of the steps described here can determine the growth rate. And if it's the diffusion that determines the growth rate, you call it mass transfer controlled growth. If it's the surface reaction here that controls the growth rate, it is called kinetically controlled growth. And now the thing that I actually was aiming at, most of the reactions can be described in this way, the Arrhenius equation. So, for instance, the growth rate goes like this: a constant times E in the power minus EA activation energy over KT, the Boltzmann constant, and the absolute temperature. Why that is not even so easy to understand, so I skip it here. It's rather complicated, but it is a lot of it makes a lot of sense to determine the EA for a specific reaction. And how do you do that? You plot 1 over T versus the logarithm of the growth rate, and the slope of the straight line you then get is minus EA over K. That determines the EA, and that tells you how sensitive for temperature variation your process is. So here's the high temperature, here's the low temperature, and if you go from low to high temperature, your growth rate increases exponentially. That, of course, cannot continue; it will explode. So at some point in time, it veers off, and that is where the reaction becomes transport limited. These kind of reactions are on the surface. They increase exponentially with temperature, and it is here where the reaction is a lot less sensitive for the temperature, where diffusion towards the surface determines the growth rate. And thinking a little bit ahead, at the moment I'm talking about conventional epi, and the high temperature range is sitting here, not very much dependent on temperature. When you move later on to low temperature epi, that is all in this region, very temperature dependent. So plotting a specific reaction like this gives you insight in a couple of things. It tells you especially the point where you move from kinetically controlled growth to transport limited growth. Common epi drawbacks. I mentioned 3 here: pre-epi bake sensitivity, auto-doping, and slip. A clean surface, that's the name of the game. If the surface is not clean, you cannot grow an epi layer, you grow defects. And a defect-free epi layer only grows on an atomically clean surface. Silicon, in contact with the air, grows a native oxide film. And the native oxide needs to be removed in the reactor, or even before you put the wafer in the reactor. Well, we used to do that by means of an HCl etch. And the HCl is not really necessary because just increasing the temperature you get the dissociation reaction. SiO2 forms SiO, which is volatile and will disappear. HCl etches the silicon. It really takes some silicon away. Why do we need HCl then? Well, in the old days, bipolar days, we were not working to the standards we're up to now. Metal tweezers, metal wafer stages. There was a very, at least compared to today's standards, the metal contamination was extremely high. And that is where the HCl came in handy. We really removed a few tenths of a micron of the surface of the layer. And with that, we removed a lot of the metal contamination. Now, with the MOS technology, we learned how to work clean. We don't need the HCl anymore. In fact, it is an HCl etch at the moment is bringing in more metals than it's removing. That is how much the processing improved over the years. So the proper epi preparation is just to bake in hydrogen to remove the native oxide, and HCl to clean the surface we don't use anymore. Hydrogen bake efficiency is determined by two things: the temperature and the partial pressures of oxygen and hydrogen. The higher, the more contaminated the reactor, the higher the partial pressure of oxygen and hydrogen, the higher temperature you need to be able to remove the native oxide. And if you do not remove the native oxide completely, insufficient removal, you get defects in your layer. It is not a big issue anymore, as I told you already. We learned from MOS processing, we learned clean processing, and what used to be a big issue in the old days, cleanliness, dry gases, is not an issue anymore. Conventional epi does not suffer from baking insufficiencies anymore, and that is purely due to the improvement in the cleanliness of the gases, of the wafer handling and everything. So high temperatures, the more contaminated the reactor, the higher the partial pressures of oxygen and hydrogen, the higher temperature you need to be able to grow a defect-free layer. And the reverse is true as well. The cleaner you are working, the lower the temperature, you can choose a temperature and still get a decent layer. So that explains the move towards lower temperatures. That has been going on for the last 20 years. Autodoping. Usually we like to grow a lightly doped layer. Here is the depth, here is the concentration on a log scale. We like to grow a lowly doped layer, high resistivity layer, on top of a heavily doped surface or on top of a buried layer. And in an ideal case, the dope transition is straight. Well, that of course, at least in conventional epi, never happens. Growing at 1150 or even higher temperatures means your dopant simply diffuses while you're growing, simply diffuses into the growing layer. And that is this section of the curve. Much more harmful is the tail here. And the tail is caused by redeposition of the dopant. Arsenic, for instance. Where does it come from? Well, when you start to grow, there's still arsenic, phosphorus, boron, evaporating from the surface. It gets into the gas flow and is redeposited. Backside of the wafer, same thing. It is not coated. If it's not coated, it will release dopants forever. So the transition width before you reach the level you want to be at can be very wide, several microns in the old days. Can we do something about it? Well, this part is easy, of course. That's very simple. That is just a temperature budget. This part is a lot more difficult. Of course, we can backseal the wafer to make sure that no dopants are evaporating from the backside of the wafer, and it helps, and it is done if it's necessary. But the doping tail is much more difficult to remove. It depends on temperature, pressure, growth rate, how quickly do you seal the top surface to stop the dopant from evaporating, and of course the vapor pressure of the dopant. Characteristics: antimony has a low vapor pressure, low diffusivity, so it behaves pretty good in terms of water doping. Arsenic, high vapor pressure, is terrible. Phosphorus is slightly better, and boron has a very high diffusivity, so the moment boron reaches the surface it tends to diffuse into the surface and there's no way to remove it anymore. And especially the anti-dopants what happens there is strongly determined by adsorption phenomena. And as a rule of thumb, when you increase the temperature, the anti-dopants, the order dope of the anti-dopants is becoming better, boron gets worse. If you reduce the pressure, the anti-dopants are getting better, boron gets worse. Can we understand that? Well, a little bit. What are the best known methods to suppress order doping? Well, for the anti-dopants, and especially for arsenic, use a maximum desorption strategy. Arsenic adsorbs at the surface, and it's very difficult to remove the adsorbed layer. When you start to grow, the adsorbed layer usually is there, and you dope from the adsorbed layer, and that is what is causing the tail. So, so what you do here, use a maximum desorption strategy. Of course, you use backsealed wafers, and then a high temperature and reduced pressure to remove, before you start to grow, to remove as much of the adsorbed layer as possible. So hydrogen baker, high temperature, very high temperature, thin capping layer to stop the evaporation from the surface. Then you drop the temperature 50 to 100 degrees and grow the rest of the layer. There's still order doping, but this is by far the best to suppress it. Boron, entirely different. Boron is an easy diffuser, it's a very quick diffuser, so what you should do is avoid boron coming in contact with the wafer. How do you do that? Low temperature. Backsealed wafer and the lowest temperature possible. And then in order to decrease the mean free path, processing at atmospheric pressure has a slight advantage over processing at reduced pressure. Low temperature, hydrogen bake at the lowest temperature, and grow at the same low temperature. And these are the strategies developed over 60 years of epitaxy. So it's not very likely that there's much to be improved here. One slide about the reduced pressure epi. Thick layers require a high growth rate. So reduced pressure epi is not LPCVD, on the contrary. It is still the same reactor, it is still the same laminar gas flow. Temperature does not go down in the millitorr range as is the case with LPCVD, but remains in the 20 to 100 torr range because you have to maintain a rather high growth rate. You want to grow several microns. So no changes in reactor geometry. We only add a high capacity pumping system. It increases complexity tremendously. It increases the downtime. It is impossible to implement a rectangular tube. The tube would implode unless it's reinforced as we do in the epsilon reactor. And it is very difficult to implement in RF heated systems because when you draw a vacuum and you reduce the pressure, you ignite a plasma. And plasma enhanced CVD comes in handy when you want to grow silicon nitride and silicon oxide. And it's a disaster for epi because it releases contaminants. And you get a very contaminated layer. So in fact, in RF heated systems, you cannot use reduced pressure. Why do we do it then? It improves arsenic order doping. That is the one and only reason that reduced epi was developed in the end of the 70s of last century. But it also has a little bit of an advantage. It improves pattern shift and distortion, but I'm not talking about that today, so we skip it. Cleaner operation in general. Why? Partial pressures. It is the partial pressure of oxygen, the partial pressure of hydrogen. Overall pressure with an order of magnitude. Also the partial pressures of oxygen and moisture go down with an order of magnitude. And that is what I mean when I write down here cleaner operation. And if you grow selectively, I come to that later, reduced pressure gives you a slightly larger processing window, but that's not very important. Defects, crystallographic defects. Slip is the one that plagues, has plagued the EPI processing. What is slip? A dislocation that has moved through a crystal or through a part of the crystal, and in effect, part of the crystal is moved with respect to the other part. And on a 100 surface, a slipped wafer will look like this. You see the dislocation lines on the four corners. If it gets worse, you also get a spot in the center where you see dislocation lines. And if it gets still worse, you see them running all over the wafer and all through the wafer. And the cause is stress, excess stress due to temperature gradient. Temperature gradient from center to edge. What is happening? Well, in case the wafer is heated by the susceptor, which by the way is always the case if you use RF heating. It's also the case if you use lamp heating from only one side. The susceptor is warmer than the top of the susceptor, which is warmer than the backside of the wafer, which is warmer than the top surface of the wafer. And the wafer curls up. The edges lose contact. Then you blow a hydrogen storm across the wafer and the edges cool even more and it comes up more. It's stressed to the point that it exceeds the yield stress and it slips to relax the stress. And after cooling down, after having grown your EPI wafer, this is what you see. And how do we overcome that? Well, heating from both sides or heating from the top, of course, solves this kind of problem. In the old days, there were a lot of RF heated reactors, so it was suggested to do something like this: a pocket, make sure that the edges are in contact with the susceptor, and yes, probably a good idea. It never worked. RF heating suffers. Well, the surface, the susceptor is not uniform enough anymore. These kind of edges generate during RF heating additional currents, and it's very difficult to apply even heating this way. The solution never worked. So we are coming by now by lamp heating from the top and from the bottom, even heating, and it is also clear that an RF heated reactor will always suffer from slip. Because if you use RF heating, the susceptor is always warmer than the wafer, and there's no solution to the problem I just sketched. The wafer has a big influence as well. There is Sobralski material, there is floating zone material. Sobralski contains a lot of oxygen precipitates. Those make the wafer strong, a lot stronger than floating zone material. So in terms of sensitivity for slip, floating zone is a lot more sensitive to these kind of defects than Sobralski is. Presence of dope layers, implantations all cause stress, so that they have an influence on slip. And any treatments prior to EPI that leave residual stress in the wafers are always, of course, are not so good to prevent slip. The same from modeling, you can conclude that the same temperatures between the center and the edge of the wafer causes slip, some 30 degrees between the center and edge, in wafers of any diameter. So that explains why slip is a lot more difficult to control in a 300 millimeter wafer than in a 1 inch and 25 millimeter. And that explains why over time slip was a problem that increased with the wafer size. Last but not least, at higher temperatures, the yield stress of the wafer is lower. The more you heat the wafer, the lower the yield stress is, the easier slip develops. So, as a consequence, the higher the temperature, the more difficult it is to avoid slip. And the present trend to process at lower temperature is very beneficial to avoiding slip lines. Low temperature epi, quite a different ballgame, I would say. When you talk about low temperature epi, I have to start with silicon germane. Silicon germane strain layer growth, a little bit about bandgap engineering. I will show some applications of low temperature epi, and to conclude with 2 issues in low temperature epi: the moisture sensitivity and emissivity effects. Silicon germane alloy layers. Fortunately, silicon and germane are mixing very well, in spite of the fact that germane has a slightly larger lattice constant than silicon, 4%. It also has a smaller band gap in silicon, 0.66 versus 1.1 electron volt, and it is the reduction in band gap we are after. So if we grow a silicon alloy layer on top of a silicon crystal, it will be strained due to the fact that it doesn't fit, and it will have a lower band gap, and that is what we call band gap engineering. So strained layer growth, 2 things can happen. Here's the substrate, say silicon. Here's the silicon germane alloy layer with a slightly larger lattice constant. The lattice constant is uniformly distributed. If you grow one on top of the other, you start like this. The crystal with the larger lattice constant adapts to the underlying silicon crystal. It is compressed and elongated in the vertical direction. And that is the strained layer on top. Now if you continue growing, you exceed, the strain builds up, you exceed the yield stress, and you generate defects, dislocations at the interface, and called misfit dislocations. Some of them are moving their way up, called threading dislocations. And it's, well, not completely unstrained, but it relaxes. Let's try to draw it a little bit here. Here the lattice constant in the horizontal plane is the same as from silicon. If it relaxes, it expands, and at the same time forms misfit dislocations. And so the critical layer thickness is an important item here. You can grow a layer strained without generating defects up to the critical limit. And the critical limit depends, of course, on 2 things: the germane content and the thickness of the layer. The higher the germane content, the lower the layer thickness before you reach the critical point. And if you reach the critical point and go over that, it will relax, get defects, unwanted situation. The band gap, silicon, germane, unstrained, but that is not what we are after. It's of course this one that we are after. We are growing strained layers. For instance, 20% germane in the silicon lattice here creates a band gap, a drop in band gap of about 0.2 electron volt. How can we use that? Well, compare 2 transistors, hypothetical. Silicon transistor and a transistor with a silicon germane base. Exactly the same for the rest. Then the band gap, the drop in band gap makes your collector current increase by this factor E delta Eg over kT, which is for 20% atomic, 20 atomic percent germane, which is more than 1,000. Well, nobody needs a transistor with this kind of gain, but it can be traded, and that is the trick. It can be traded for high cutoff frequencies. The high cutoff frequencies, that is where everybody was after in the mid 80s. HBTs, high heterojunction bipolar transistors, cutoff frequencies in the 100 gigahertz to replace gallium arsenide. It can also be exchanged for low base resistance, for low noise, and a couple of other good things. What you also may be able to see is that the transistor with silicon germane base has an improved low temperature operation. Because the T is in the denominator here, it does not suffer from the runaway effect of a normal transistor that increases the current and it eats up and it destroys itself. This one does not, but it's a minor effect. So, yeah, everybody was after silicon germane, and in order to grow silicon germane, you need to keep the temperature below 700, maybe 800 degrees, but that is about the maximum temperature. If you don't do that, incorporation of some germane in the crystal is insufficient. You get silicon and germane into diffusion, and there is a higher risk of relaxation. Well, these kind of temperatures in those days were totally incompatible with conventional epi growth. We were used to temperatures, well, 1100 at the lowest. Lower than that, we used to get defects. So a gap of 300 degrees at least between what we could do and what we would like to have. Well, the principle of the HBT was proven by MBE, molecular beam epitaxy. Molecular beam epitaxy is nice. You can grow all sorts of nice profiles, silicon germane HBTs with high cutoff frequencies. The only problem is it grows about 1 wafer per shift. So in a 24-hour day it grows 3 wafers and that's it. Not fit for production. So there was a drive towards low temperature epi growth. And how was it solved? By, in first instance, by Meyerson, IBM. He picked up some old papers and determined for himself that the main reason that we could not lower the temperature in conventional epitaxy was due to the background of moisture primarily. He extrapolated his data and came to the conclusion that it should be possible to grow epi at 600, 700 degrees, provided you've got the partial pressure of moisture below 10, minus 11, 10, minus 12 torr UHV. Well, that's what he did. He built himself a UHV CVD reactor, and he indeed managed to grow silicon germane epi in CVD mode, kind of LPCVD, UHV CVD. It worked. Those reactors were sold. But there was another opportunity, another possibility. Ironically, when that happened, the reactor that could do it all existed already. Early 80s, it was predicted that MOS, I mentioned it, that MOS needed epi. So every manufacturer of epi equipment tried to pick up that market, and they were all developing new reactors. The Pi Materials did it, Gemini did it. And we did it at ASM as well. Well, Gemini never made it to the end. They showed a picture of something that you could see at first sight would never work, and it indeed never worked. The Pi Materials came with a reactor, huge. Just it blown up the old barrel to a size 2 stories high. Enormous power. I think they built only 10 of it, and that was it. Well, the ASM single wafer reactor existed, and in those days, was a high need to do something better than UHV CVD, because UHV CVD in production is very difficult to maintain. And I thought, well, this new reactor, let's see how low we can go. And I got a week of reactor time at ASM by the time I had joined Philips research lab. I got a week of reactor time at Phoenix, put the wafers in, and well, the rest is history. It worked from the first moment on. It got very nice in. Why I come to that later. And it is like I said, it is very different from conventional EPI. We are in the kinetically controlled mode, growth mode now, low growth rates, no diffusion, very thin layers, single wafer reactors, extremely, because we shifted the problem. The problem we originally had in the 60s, already at 1150 degrees, high moisture content. Everything got better, but now we have it at 700, 650 degrees, extremely moisture and oxygen sensitive, and we do it at 10 to 50 torr. And well, the process allows the growth of silicon germane alloys on pattern wafers because of the low temperature. Diffusion does not play a role anymore. Here is about the first attempt to grow silicon germane in an epsilon reactor at atmospheric pressure in those days. Absolutely perfect. Well, not just from the high resolution temp, because it shows you only a very small section of the crystal. You see how sharp the transitions are. The dark coloration, by the way, is caused by the strain. Substrate, silicon germane layer, silicon capping layer. And if that works so well, how do our dopes look in the same way? A doped silicon layer with an undoped capping layer on top. Sims plot, here's the thickness, here's the concentration. And you see a very nice profile for boron. By the way, the slopes here are totally Sims determined. And the transition, dope transition is so sharp that there is no Sims that can resolve the slope here. The same is, by the way, is true for silicon, the same is true for carbon. Extremely steep transitions. So the auto doping that we used to suffer from is totally gone. For boron. For phosphorus, you see already different. The slope here is still steep, but not as good as for boron, and no longer and it's no longer Sims determined. This is real, but still a very nice profile. So phosphorus can be used. Arsenic, terrible, totally uncontrollable. It comes up slowly. You cannot even determine where the arsine line was turned off. I explained that already. There is an adsorb layer, and when you stop adding arsine to the gas flow, the layer still is doped from the adsorbed layer and comes down very, very slowly. When you cut off the growth here, there is still a pile of arsine on top. So arsenic cannot be used, controlled in a low temperature mode. Phosphorus can, but only at atmospheric pressure. If you go to reduced pressure, the same happens. You get a profile like this. Why is that? Well, like I said, we are in a totally different regime now. It is the high hydrogen pressure that takes over the sides from the phosphate. At reduced pressure, the partial pressure of hydrogen is not enough, and the lattice sites are occupied by adsorbed phosphor. And when you increase the hydrogen pressure, hydrogen takes over, removes the phosphorus, and that is the way phosphorus can be used. By the way, that is the same, well, I come to that, I think. Yeah, well, here's another example of a nice phosphorus profile, starting at high concentration, a staircase, showing, again, good, almost perfect control, but at atmospheric pressure only. Now, carbon used to be a contaminant in conventional EPI. It creates defects, it forms silicon carbide. At low temperature we can use carbon to our advantage. It is used to maintain a block-shaped boron profile. Boron is an easy diffuser. Diffuses at low temperatures, and in order to keep the nice profile post-processing at higher temperatures, we use carbon. Added a concentration of 0.1 to 2 atomic percent, it traps interstitials, and in doing so, it limits the out diffusion of boron. And we do that with methylsilane. If you use too much carbon at high concentration, the epi layers are getting rough and defects start to develop. But it is very nice to be able to control the out diffusion of boron. What do you think happens in a conventional reactor, batch reactor, when you put a 100 and a 111 wafer next to each other, make the run? Any change in thickness? There isn't, because it is transport limited. It is the transport to the surface that limits the growth rate, no matter what you put in there, 111, 100. Totally different at reduced temperature, at low temperature. Here is a 111 and a 100 wafer. 100 is the red one. A silicon germane layer with a silicon capping layer. And you make exactly the same run on a 111 wafer, and you see the difference. So the silicon germane growth rate is a lot lower on 111. The silicon growth rate is about half of what it is on 100. And the boron dopant incorporation, because the silicon capping layer is boron doped, is almost in almost an order of magnitude higher. So totally different from what they're used to in the conventional epitaxy. An example of an HBT, the base profile, rather complex. Boron spike in silicon germane, and with the carbon around the boron to keep the boron from diffusing. And to show you how complicated it is, substrate, thin layer of intrinsic silicon, silicon germane, high germane content, silicon germane carbon. We introduce the boron spike, carbon again, silicon germane carbon again. We move to a section with a lower concentration of germane and put a silicon capping layer, boron doped silicon capping layer on top. 7 layers altogether. Compare that to the conventional single silicon layer, and conclude that it has become a lot more complicated. Here an example of an HBT in cross section in deep and shallow trench isolation. Here's the deep trench, here's the shallow trench, because we cannot use, of course, PN junctions to isolate because of the capacitance. Here's the transistor, emitter, base, collector, contacts. Slightly higher magnification. Here's the pedestal, which again here. The transistor. 3 times epi, because here is the conventional epi layer, pretty thin, 1 micron. Here is the base stack, the silicon germane base stack, grown at low temperature, silicon germane, silicon capping layer. Then the rest of the structure is made, the nitride spacers, and then it enters the reactor, the epi reactor, for a 3rd time for an arsenic doped mono-emitter. Usually poly emitters are applied, but this one actually has 3 epi layers. Twinned areas, well, you see some recrystallization that explains the silly shape of the mono-emitter. It is grown to here, and then post-processing the polysilicon here recrystallizes and forms this. Why do we use a mono-emitter? To reduce the emitter base resistance. Intricacies. I call them intricacies. Why? Because the word said what are intricacies? Difficult to understand because of the complicated nature of things. Well, that very much describes the moisture sensitivity and the emissivity effect. Moisture sensitivity. Why I did not tell you why suddenly an existing reactor was doing so well in low temperature epi. That is because what is wrong with the UHV? Well, nothing is wrong. It's probably very true that you need UHV conditions to keep the surface from oxidizing, but the experiments in those days, where the literature came from, was done in vacuum. And we are working with a rather high pressure of partial pressure of hydrogen. And it is the high partial pressure of hydrogen that protects the surface. We always we do not lose our hydrogen protection at about 450 degrees. This happens in vacuum. With a high partial pressure of hydrogen, we maintain the hydrogen coverage up to 700 degrees or more. That is what protects the surface. So baking the surface may not even be effective anymore at 800 or 700 degrees C because you're at the wrong side of the equilibrium. It is the hydrogen protection that saves us, and it is the hydrogen protection that allows reactors like the epsilon reactor to be fit to grow low temperature epi. And having said that, the sensitivity for moisture and oxygen is not so extreme that we need UHV, but low temperature epi is and remains a very critical process. What helps us here, gas purifiers, 10 ppb rating at the moment. We started off in the early days with 1 ppm, so huge improvement there. Clean gas handling, and above all, and that is important, load locks. All reactors except the epsilon opened to atmosphere for loading and unloading. What happens then? You trap moisture inside, moisture condenses, adsorbs at the cool surfaces, the cool flanges. You put the wafers in, you start heating, and moisture desorbs, is released during the process and spoils the thing, spoils your low temperature processing. So it is the gas purifiers, the gas handling, but above all the load locks that allow us to grow low temperature epi in an epsilon or epsilon-like reactor. Equipment to measure the moisture levels was not available. The last couple of years there are some tools that allow you to measure really moisture in the ppb range. It may not be of a lot of use in an epsilon reactor because it suffers from its HCl. Your precursor contains HCl, H2Cl2. You're etching the surface, so there's always HCl released, and the sensors may not withstand HCl. But at least there is some equipment becoming available. The best monitor up to now, my feeling, is the wafer surface. It indicates when the conditions are not adequate anymore. It gets rough, and it gets worse. You start to see defects. Nevertheless, it can be very difficult and time-consuming to pinpoint the problem. It is very difficult to sort out what is causing a bad surface. Is it the quality of your process gases? Is it a leak? Difficult. So as long as your layers are nice and shiny, knock on wood and keep it that way. To conclude with an even more intricate problem, emissivity. What growing epi, there are distinguished between several cases. Conventional blanket layers, substrate, you grow an epi layer on top. We can grow selectively. There is oxide mask, the windows in the mask, you grow epi, and the oxide remains clean. A blanket layer, same thing, but now you grow on the oxide as well. And last but not least, unibond wafer, buried oxide layer with a monosilicon layer on top. And then you grow blanket epi, in fact, like you do here. How do they behave in terms of emissivity? Well, emissivity, the wafers are heated by lamps. The higher the absorption of the wafers, the more it heats up. And the emissivity plays a role there. Conventional epi, no change in emissivity. You grow and the emissivity doesn't change. If you grow selective epi, the emissivity is different because there is a refractive layer on top. It's different, but the emissivity does not change during growth. You are only growing in the windows. This is the worst case. You deposit blanket silicon on top of silicon oxide. A very effective interference filter, and you're changing the filter. So your emissivity is changing during growth. Now, back to this one. These are the situations. This one is easy, no change. This one is easy when you grow. It is a different emissivity from this one, but there is no change when you're growing. These two are very difficult. When you're growing, your emissivity is changing. And we got a hunch, well, we're running selective epi. We saw all sorts of growth rate variations that we could not explain, and we thought we were bothered by loading effects. And at some point in time, almost identical mask, we saw a difference, so it cannot be loading effects. What else can it be? Emissivity, maybe. How do you compare that? Well, these two are not on a wafer like that, because you're growing poly here, and you're growing poly thickness to epi thickness. It's not a good comparison. These two are ideal to compare in a growth rate experiment. Same top surface, 100 silicon. This one has a different emissivity than this one. So that was the experiment we did. We deposited an epi layer, and at fixed time intervals we inserted the boron layer. The blue one is the silicon wafer. The red one is the one with the buried oxide. Nope. Exactly the same run. Well, you see the difference. There is a clear difference in growth rate. One is much thicker than one layer is much thicker than the other. You can even plot the growth rate in the intervals, and you see a little bit what is happening. On the N+ wafer, your growth rate is constant. Here, you start very low and you increase because and you're probably growing through one or two swings. And then the top layer of silicon is thick enough, and then you approach the emissivity of the N+ wafer again. These kind of differences indicate the temperature difference of at least 30 degrees, which is considerable, and which is pretty bad for your processing. And at the time I thought it was a complete disaster, because in the lab I was getting different masks every day, and each one needed to be characterized. I thought it is not going to work. To my surprise, in a production situation, people don't bother. Some don't even know that this effect exists, because they are running the same mask day after day and again. And when you get something else after a couple of months, they tune it in again, and they don't even realize that this is going on. Because the temperature increases while you're growing, and while you're doing that, you're changing your main content, you're changing the dopant incorporation, but apparently it bothers nobody. And well, so let's keep it this way, but it's not a nice effect. And now, you think that you understand emissivity effects. I'm afraid you don't. There's one step more here, because the temperature in the center of the susceptor is constant. It is controlled by a thermocouple. And no matter what you do to the wafer that is on top, it will control and always maintain fixed temperature, the set point, in the center of the susceptor. Now, what is causing the temperature change then? It is the changing thermal flux. You're shifting when the emissivity changes. more or less heat is absorbed by the top, from the top heater, and the bottom heater has to compensate. So you're shifting your heat flux. Less heat coming from the top means more from the bottom. And the thermal resistance that exists between the center of the susceptor and the wafer causes the terrible change in temperature. Like voltage drop over a resistor, this is temperature drop over a thermal resistor. And so, yeah, well, due to the thermal flux, the wafer temperature varies with its varying emissivity. And the consequence is that a different pattern or a different thickness of the layer stack gives rise to a different wafer temperature. Not so nice, a lot less of a problem than I at some point in time thought it was or it would be. And there are possible solutions. Why do we see this only at reduced temperature? Because that is the section where we are extremely sensitive for temperature variations. On top of that, at low temperature, more of the heat transfer is by conduction. At high temperatures, it's radiation. Less sensitive. That is less sensitive for these kind of effects. And of course, we use only at low temperature. We use patterned wafers. It only happens on patterned wafers when we grow on oxide. Concluding remarks. Few. Modern epi reactors are very sophisticated tools, in spite of the fact that they are all based on the at least 50 years old horizontal reactor. All the nice improvements we saw in the end of the 70s, beginning of the 80s, LPCVD, that meant the horizontal reactor for nitride and oxide wasn't used anymore. LPCVD was much more uniform, much better process. Shortly after that, plasma enhanced CVD lowered the temperature. It all did not happen for EPI. EPI needed a high growth rate. Plasma does not work to our advantage. So we are in fact still stuck with the technology of 50, 60 years ago. Yeah, conventional EPI, I started with, is almost as old as the semiconductor industry. It does not contain surprises anymore. There's not much to improve there, I'm afraid. Not true for low temperature epitaxy, which is much more recent. There is a lot that still needs to be characterized, and its secrets are not yet completely uncovered. What we could use better, I think, is the unmatched capability of low temperature EPI to grow almost any arc doping profile. When we started all this, at the lab, I got requests to grow anything, Bragg mirrors, quantum wells, any arc profile, and suddenly that died away. Everybody focused on HBTs. I think it's time for the people that are involved in transistors to think about different profiles. It's very possible to do something nice here. So, having said this, yes, the reactor is, the prototype was up, of the epsilon was up just about 30 years ago. 30 years with one reactor is a lot of time, longer than any reactor before that performed. So it's about time that something new comes aboard. But improvements can be made. For instance, I would like to run a reactor without a susceptor, increase the throughput, get rid of the graphite, the silicon carbon coated graphite makes the tube cleaner. But yeah, well, it requires some attention. And there are more improvements that are possible. A new technology, maybe, I wouldn't know what, but maybe possible. So if you want to spend some time in CVD, well, yeah, I think there's sufficient to be done. And that's what I want to conclude with. Thank you.